Hi there, you're listening to the Hellenistic Age Podcast, Episode 99, Hellenistic Science, Geography, and Astronomy. Humanity has always wondered about its place in the universe. Since our earliest ancestors started to recognize patterns in the night sky, we have looked to the stars in order to better understand not only the nature of the cosmos, but also about this pale blue dot that we call Earth. In the Hellenistic period, astronomy and geography were common topics of study for the many scientific thinkers working at the time. The campaigns of Alexander fundamentally changed the Greek understanding of the inhabited world, as explorers sought to chart new lands and peoples they now interacted with or ruled over, taking them as far as India and Iceland. New developments in mathematics and access to the records of those like the Babylonians enabled astronomers to propose rational explanations behind celestial phenomena, or create astonishingly advanced instruments to calculate those events. Today's episode will conclude our series on science and technology during the Hellenistic Age, as we talk about the changes in how the thinkers understood the cosmos and the Earth itself. To begin with, let us start with geography. Perhaps our most important source on Hellenistic geography is Strabo of Amasea, a Greek born to an affluent family in the Mithridatic kingdom of Pontus in 64 BC. Following his family's defection to the Roman Republic, Strabo enjoyed a lengthy career traveling around much of the eastern Mediterranean as a scholar, and around the turn of the millennium he composed a massive work known, appropriately enough, as the Geography. Across 17 books, he surveys the entirety of the known world from Britain to India, providing an account of the landscape and customs of the peoples who dwelled within them, along with anecdotes and scientific discussions. Most important for our purposes, he almost single-handedly preserved the writings of dozens of geographers from the Hellenistic period, which otherwise would have been lost entirely, and our understanding next to nothing. During the Archaic and early Classical period, the Greeks believed that the Earth consisted of a singular landmass surrounded by the ocean, a flat plane like you would set a compass upon a map. Though they believed themselves to be the center of the civilized world, Greek explorers and sailors were beginning to get a broader understanding of the wider world outside of the eastern Mediterranean, and quickly realized that their framework was too simple to be true. In the 6th century, Anaximander was the first known Greek to conceive of the Earth as being more three-dimensional in shape, making it analogous to the section of a column, round with two flat surfaces, and was the first to create maps that were based on this model. Shortly afterwards, the Pythagoreans popularized the concept of a spherical Earth in the 5th century, a view supported by later philosophers like Parmenides, Plato, and Aristotle. The extent to which the Greeks understood their world was termed oikoumene, the inhabited world, where civilization resided. Naturally, Greece was at the very center, and the further you go in any direction, the more barbaric the peoples and less hospitable the lands would be. The landmass of the oikoumene is often described as chlamys-shaped, referring to a military cloak that formed a trapezoid-like figure, encompassing their understanding of Europe, Africa, and Asia, along with a great ocean that surrounded them. The campaigns of Alexander the Great and his generals greatly expanded the Greek knowledge of Asia and Africa. Surveyors, known as bematists, accompanied the army recording the distances of the newly subjugated territories, while high-ranking members of the court were commissioned to explore the furthermost regions and record their findings. Alexander's boyhood friend and naval commander Nearchus wrote a book on his travels in the Indus River, Indian Ocean, and Persian Gulf during the final years of the campaign. The Seleucid official Megasthenes was dispatched to the court of Chandragupta in modern Patna, while the admiral Patroclus sailed through the Caspian Sea. There was still a degree of fantasticality to the accounts of these men, perhaps influenced by the political nature of their work, but it nevertheless represented a turning point for the Greek and later Roman understanding of the lands beyond the Mediterranean. While all this was focusing on the Asian and African land masses, another expedition was taking place in the opposite direction. At the time of Alexander's conquests, a Greek explorer named Pytheas of Massalia embarked on a voyage that took him from modern Marseille to Brittany, before sailing the Atlantic around the island of Britain. Perhaps he reached as far as Iceland, what he called Thule, before returning to the Baltic Sea and passing through Norway. His work documenting his findings on the ocean has not survived, and we know almost nothing about the man himself nor the purpose of his trip. Some writers like Strabo and Polybius are skeptical over his findings, but the preserved excerpt suggests that he had scientific interests based on the observations he made while traveling. Unlike the Mediterranean, the Atlantic Ocean experiences far greater tidal fluctuations, and Pytheas correctly deduced that the waxing and waning of the moon had an impact on its intensity, especially with regards to a full or new moon. He was also the first Greek to observe a midnight sun, the phenomenon experienced by those living near the poles where daylight continues uninterrupted at the height of the summer solstice. Much of this information is quite credible, and Pytheas made sure to provide evidence by locating his position geographically by measuring the sun's shadow at various points throughout his itinerary. The reports of these men would eventually be collected and serve as the basis for much of the research compiled by later writers, who were often unable or unwilling to visit these regions themselves, and the most important Hellenistic geographer was Eratosthenes of Cyrene. Born in 275, Eratosthenes was a highly educated scholar that served the Ptolemies 3 through 5 as a royal tutor and head of the Library of Alexandria until 196, when he starved himself to death after going completely blind. Unlike his colleague Archimedes, he was never known during his era as a specialist in any one field, but he dabbled extensively in a wide range of subjects like mathematics, astronomy, literature, and many others. This earned him the nickname of Pentathlos, talented in multiple areas and master of none, though some harsher authors refer to him as Beta, number 2, since he was never first in his field. But we may consider him to be the most influential geographer of the period. He was the one to actually coin the term geography, and while he received criticism for relying on the accounts of other travelers rather than making his own observations, his legacy would quickly be cemented. Unfortunately, his works are lost, but his feats were preserved by those like Strabo, Vitruvius, and the astronomer Cleomedes, with the most famous being the calculation of the Earth's circumference in his treatise on the measurement of the Earth. In the city of Syene, located near the Nile's first cataract in the Aswan, Eratosthenes learned that there were no shadows cast by sundials or any other towering structures during noontime on the summer solstice. Yet if you were in Alexandria, you would find shadows measuring 7 1/5 degrees at that exact moment. This was quite peculiar, but not unexpected. A spherical Earth would produce this effect, and Greek scientists had long understood that the curvature of the Earth resulted in different zones, bound by the Arctic Circle in the north and the Tropic of Cancer in the south, that could affect astronomical observations. Sailors navigating the oceans would have empirical evidence of this phenomenon when the positions of stars would change depending on how north or south you were. With this realization, estimations on the Earth's circumference came not long afterwards. Aristotle suggested 400,000 stadia in length, while the post-Alexandrian thinker Hipparchus brought it down to 300,000 stadia. Eratosthenes was the first to devise a system of organized divisions based on meridians, more specifically latitude, running north to south, and longitude, running east to west. As we mentioned earlier, Pytheas made measurements of the sun's height during the winter solstice, and astronomers in the following centuries were able to calculate the latitudes based on this data. Eratosthenes took it a step further by establishing a prime meridian running through Alexandria, going south as far as the Nubian city of Meroe, while the northbound portion passed through Rhodes, the mouth of the Dnieper River, and lastly Thule, courtesy of Pytheas' calculations. He believed that Syene and Alexandria were located on the same latitude, though in reality there is a 3-degree difference between the two, and he measured out the approximate distance between the two cities as 5,000 stadia. Since the Earth is a sphere, albeit an imperfect one, a full circumference should be 360 degrees, and it just so happens that 7 1/5 degree is equal to 1/50th of 360 degrees. As such, if we multiply 5,000 stadia by 50, we get a total of 250,000 stadia. The exact value of a stadium depends upon the author, but the approximate range falls somewhere between 39,000 and 47,000 kilometers, or 24,000 and 29,000 miles. For perspective, the actual size is measured at 40,070 kilometers, or 24,898 miles, meaning that Eratosthenes came astonishingly close to the true value by just using simple mathematics and tools available in his day. As we alluded to earlier, the Cyrenaean scientists had done considerable work on a system of latitudes and longitudes, using them to build a new map of the oikumene. A grid would overlay this map, with the meridian points often falling on some of the most important cities of the Mediterranean, and more distant locations were inferred from the research of early explorers like Pytheas and Alexander's officers. There were flaws with this model, as he often had to rely on the accounts of others that didn't have the same level of precise measurements, and the world map stretches to better fit his parallel lines. Still, it was a remarkable step in the right direction. With the globe covered, let us turn to the study of the stars, known as astronomy. We must differentiate astronomy from something like cosmogony, which is the explanation of the origin of the universe. The works of the 8th century poet Hesiod would be the earliest example of cosmogony in the Greek tradition. In astronomical terms, the cosmos was a rational organization of heavenly bodies, and has always existed in some capacity. Astronomers looked away from theistic interpretations, arguing instead that these planets and stars were material objects, and sought to explain and predict their movements. Throughout antiquity and beyond, the prevailing framework of the universe was one of geocentrism, that the Earth is the center of the cosmos, and the various celestial bodies orbit us in a series of concentric rings. They had to be. How could you explain phenomena such as eclipses where one celestial body passes in front of another? Starting from the Earth, the order of distance from closest to farthest objects in these rings are as follows: the Moon, the Sun, Mercury, Venus, Mars, Jupiter, Saturn, and finally any other star formations. This framework was developed across several generations of thinkers, including Thales, Plato, Aristotle, and most importantly, Eudoxus of Cnidus. There was one individual who challenged this notion, and his name was Aristarchus. Born around 310 BC on the island of Samos, Aristarchus was a prominent mathematician and astronomer who served as the second head of the Lyceum in Athens. We have one surviving work on the sizes and distances of the Sun and Moon, in which the Samian astronomer managed to calculate those values by following simple yet clever methods. Firstly, when the Moon is at the half-moon phase, there is a perfectly straight line cutting vertically through its face, which can be drawn down to the Earth. In Euclidean fashion, the line between the Earth and the Moon, the line between the Moon and the Sun, and the line between the Earth and the Sun forms a right triangle, with the distance between the Earth and the Sun being the hypotenuse, at a right angle forming at the line on the Moon. This means that the angle between the Moon and the Sun should be less than 90 degrees, and based on his observations, Aristarchus cites the angle of 87 degrees. With the implied ratios of the sides, Aristarchus calculated that the Sun is between 18 to 20 times further from the Earth than the Moon. It actually is closer to 400 times further away, but Aristarchus' error can be largely attributed to the limitations of measuring with the naked eye, since the actual angle is 89.853 degrees, but the method is still quite sound and gives a similar value when adjusted. Another accomplishment was determining the diameters of the Sun and Moon by observing an eclipse. During a lunar eclipse, the Earth is between the Sun and the Moon, meaning that the Earth casts a shadow upon the Moon. Aristarchus recorded the time it took for the Moon to pass through the Earth's shadow, measuring its position just before and just after the eclipse. This formed an angle between the Earth's shadow and the distance to the Moon, and through a series of calculations he concluded that the diameter of the Moon must be 1/3 of that of the Earth, which is quite close to the actual value of about 1/4. He applied the same logic to determining the size of the Sun, though using that ratio of 20 he calculated earlier he came to a less accurate result, asserting that the Sun is 7 times larger than the Earth, when in actuality it is 109 times larger. Yet none of Aristarchus' surviving writings record what was his most controversial and prescient theory. Preserved in a mathematical treatise, Archimedes of Syracuse provides the only detailed account of his teachings. Quote, "But Aristarchus of Samos brought out a book consisting of some hypotheses, in which the premises lead to the result that the universe is many times greater than that now so called. His hypotheses are that the fixed stars and the sun remain unmoved, that the earth revolves about the sun in the circumference of a circle, the sun lying in the middle of the orbit, and that the sphere of the fixed stars, situated about the same center as the sun, is so great that the circle in which he supposes the earth to revolve bears such a proportion to the distance of the fixed stars as the center of the spheres bears to its surface." End quote. Aristarchus' model, whereby the earth revolves around the sun, is the oldest known model of heliocentrism, nearly identical to the one that was successfully articulated by the Polish polymath Nicolaus Copernicus 1800 years later. Despite ultimately being correct, it is rather curious that a geocentric universe remained the prevailing theory for the next several centuries. An astronomer named Seleucus of Seleucia was a strong advocate for it during the 2nd century BC, but his methods of proof were not recorded, and it is possible that he was the only one to openly champion the idea. A passage from Plutarch tells us that the contemporary Stoic philosopher Cleanthes of Assos was greatly offended by the heliocentric concept, going as far as to suggest that Aristarchus be charged with impiety for diminishing the specialness of the earth, and dedicated the whole work to trying to debunk his ideas. It is tempting to envision this as a case of religious dogma versus reason, but the pro-geocentric astronomers made their arguments on the grounds of logic and their own observations. It was reinforced under the presumption that if the Earth was the one in orbit, it would mean that it was moving at a great speed given its size. With only the naked eye, we can certainly tell if we are moving if we are sailing in a boat or riding a horse, yet there appears to be no observable effects from the planet being in motion. Still, his contributions were widely respected. Vitruvius considered him worthy enough to be ranked among those like Archimedes and Eratosthenes in terms of brilliance, and while it was unlikely that his work inspired Copernicus, he was certainly a man ahead of his own time. The other great astronomer of the Hellenistic period was Hipparchus of Nicaea. Living during the 2nd century, almost nothing is known about his life, and we lack any of his works outside of a commentary. He was extensively paraphrased though, particularly by Claudius Ptolemy. Active in Alexandria during the 2nd century AD, he is one of the most influential writers in the history of Greco-Roman science. His largest work is known as the Almagest, an enormous treatise that codified the prevailing Greco-Roman astronomical model for the next millennia. Here he builds upon much of Hipparchus' ideas into his system, and also gives us an idea of what the Nicaean astronomer was up to. One laborious accomplishment was creating the first known star catalog, with nearly 850 entries logging their relative positions to other celestial objects like constellations. This includes the observation of a new star, perhaps the result of a nova in 134 BC. Unlike Aristarchus, Hipparchus firmly believed in the notion of a geocentric universe, but he did recognize that there were problems with the model of concentric spheres. If the sun did in fact revolve around the Earth in a perfect circle, then the length of each season should be equal. His observations demonstrated that the time between the solstices and equinoxes are not the same. For example, the time between the summer solstice and the autumnal equinox is 92.5 days, but the autumnal equinox to the winter solstice is only 88.5 days. To address this, two models of motion were introduced, known as the epicyclic and eccentric motions. Originally conceived by Apollonius of Perga, who made an appearance in our episode on mathematics as the pioneer of conic sections, his work was expounded upon by Hipparchus. In an epicyclic model, a celestial body travels along a concentric circle around the Earth, but while doing so, it's traveling on its own smaller circle at the same time. The center of this deferent circle remains fixed on the circumference orbiting the Earth. Fans of amusement parks can find a parallel in the spinning teacup rides. While you can pilot a teacup and rotate it in a circular fashion, you're still following the fixed path of the ride as a whole, regardless of where you are at or how fast you're going along that smaller orbit. The other type of movement is eccentric motion. In this model, the celestial body remains fixed along a path and is not able to engage in its own orbit in deference to the main circle. However, while it does circle the Earth is not the center of this orbit, leading to inequalities in position relative to where the orbiting planet is at any one time. Hipparchus and Ptolemy found either case to be an appropriate choice to explain how the sun's movement causes variations in seasonality while still being geocentric. This could be used for the sun and the moon, but Hipparchus found it difficult to explain the motion of planets. When observing Mars or Mercury, there is a point where they can be described as being in retrograde, when the movement of the planet suddenly seems to shift and go backwards. This makes perfect sense in a heliocentric model, since in reality it is an illusion created by the Earth's own orbit of the Sun when viewing another planet. In the case of geocentrism, not so much. In spite of these problems, the geocentric model pushed by Hipparchus and later Ptolemy would remain the standard view for the next 1700 years. Hipparchus's other great feat was to discover what he describes as the precession of the equinoxes, referred today as axial precession. This is the phenomenon whereby the rotation of the Earth around its axis shifts, wobbles, because it is an imperfect sphere, where the slight bulging around the equator causes it to behave like an unbalanced spinning top. As a result, the position of the sun and stars change over time, particularly the equinoxes. However, this process is extremely slow. For the position of the sun to shift 1 degree from our point of view, equivalent to 1 day on the calendar, it would take roughly 71 years, while 1 full cycle takes approximately 26,000 years. Hipparchus realized this by comparing his own observations during the 130s BC to those of Greek astronomers working in the late 4th and early 3rd centuries, then finally going into the archives of Babylonian astronomers who recorded their findings even earlier. Here he determined that the star of Spica, the brightest in the Virgo constellation, had shifted by about 2 degrees from the early 4th century until his day, and from this he suggests that the precession occurs by 1 degree every 100 years as a low estimation, while a higher one could be 1 degree every 80 years. This is quite close to the actual value of 71 years given the limitations of the time, and Ptolemy later compared this to his own observations nearly 300 years after Hipparchus's day, and found his insights to be reasonable. Greek scholars were very willing to admit their debt to the Babylonians, whom they referred to as Chaldeans. Mesopotamian astronomy went back over 1,000 years, with tablets known as the Enuma, Anu, and Enlil recording celestial phenomena as far back as the 18th century BC. After the conquest of Alexander and rule by the Seleucids, Babylonian scribes continued to perform much the same work as their predecessors had done. Observations of celestial phenomena were recorded in cuneiform on clay tablets, including some of the first documented sightings of Halley's Comet in September of 164 BC, and copies of the Enuma, Anu, and Enlil were being published as late as 194 BC. Strabo lists the names of Babylonian astronomers who were active during the Hellenistic period, and the most prominent was Seleucus of Seleucia, who we already have mentioned was a defender of Aristarchus's heliocentric model. Like with Pytheas of Massalia, Seleucus correctly identified the relationship between the moon and the Earth's tides, also observing that not all oceans or bodies of water are affected equally. This may have been part of his defense of heliocentrism, and our few glimpses of his work lends credence to his highly respected reputation in antiquity. It is evident that Hellenistic and later Roman astronomers valued the findings of their earlier Mesopotamian counterparts, with a number like Hipparchus and Ptolemy directly citing their work. One of the longest-lasting contributions of Babylonian science to the Greek understanding of the cosmos were their attempts to determine the influence that celestial phenomena had on our lives, more commonly known as astrology. In the modern day, astrology is typically seen as either an amusing pastime or a potential grift by the unscrupulous, with no scientific basis backing it up. Ancient thinkers believed otherwise, and astrology is rarely divorced from what we would call scientific astronomy, with both terms being essentially interchangeable. Mesopotamian astrology had been practiced for millennia, But the best evidence comes from the Hellenistic period, where nearly 300 years of astronomical diaries have been preserved. It was they who divided the ecliptic, the orbital plane of the Earth as it goes around the Sun in a 360-degree fashion, into 12 parts, each representing a sign of the zodiac, and attributed significance to the position of the stars and what omens they foretold. Berosus, the Babylonian official who wrote the now fragmentary Babyloniaca on behalf of his Seleucid patrons, was traditionally named as the key figure to introduce Mesopotamian astronomy and astrology into the Greek-speaking world. Reportedly founding a school on the island of Kos, he is also said to have invented a new type of sundial, and was gifted a statue in Athens for his predictive abilities. If we are to accept that there existed a school, then there is some evidence that Chaldean may not always mean that they were Babylonian. A 2nd century inscription found in Thessaly honored a Chaldean astronomer named Antikythera, who was born in the Syrian city of Hierapolis, which could suggest that the title may have been much as an indicator of an astrological school rather than an ethnic designator. Still, astrology was considered to be a strictly Babylonian art until years later, and Chaldean astrologers held the greatest prestige. There are a few instances of them being involved with the royal courts of Hellenistic dynasties. According to tradition, Seleucus I consulted with the Babylonian priests when looking to establish a favorable time to build his new royal capital of Seleucia on the Tigris, but in this case, they attempted to mislead him in order to preserve the prestige of Babylon. Berosus, of course, served in the court of Seleucus and Antiochus I, but there does not seem to be instances of him acting in the role of astrologist for his patrons. Outside of Mesopotamia, Polyaenus speaks of a Chaldean named Sudines, who is said to have looked at the omens for Attalus I of Pergamon prior to his great victory against the Galatians. Over centuries of contact and through the teachings of those like Berosus, astrology was absorbed and further developed by Greek thinkers, who cultivated what we would call classical astrology. The key difference is that in Mesopotamian astrology, the movements of celestial bodies and other events were viewed as messages from the gods. In Hellenistic astrology, the motion of the planets was seen as a physical cause of changes in our lives, a seemingly more rational explanation outside of divine intervention. This reconciled Babylonian teachings with Greek schools of philosophy, which stressed the planets as material objects, but with the power to influence our existence. This involved the charting of a horoscope, which used information such as the position of the sun and moon on the subject's date of birth to determine what future events were to transpire. The oldest and largest known horoscope can be found on Mount Nemrut in Turkey, belonging to Antiochus I of Commagene, whose famous reliefs dot the mountain and capture a snapshot of the night skies on July 14, 109 BC and January 29, 91 BC. It is also clear that much of these developments took place in Ptolemaic Egypt as well. A ceiling slab from the Temple of Hathor in Dendera, now in the Louvre, shows the earliest depiction of the zodiac, dating to just before the reign of Cleopatra VII. Some may have pointed to its ancient origins as a sign of its legitimacy, but not all were so approving. According to a Byzantine encyclopedia, astrologers looking to practice in Alexandria were ordered to pay a tax known as the tax on the fools, not because the astrologists themselves were considered stupid, but rather the clients who consulted them. We find many critics in the Roman Republic. Cato the Elder found the idea of using astrologers for important matters like farming to be repugnant, and Cicero penned an entire work to try to debunk it as a pseudoscience. The Senate even went so far as to issue an edict in 139 BC, expelling all Chaldeans from Italy out of fear of their corrupting influence. Nevertheless, these astrologers continued to successfully ply their trades well into the Roman Empire and beyond, as even learned men like Vitruvius saw it as a fundamental science. The study of the constellations was also developed further at this time. The poet Eratosthenes of Soli, who worked at the court of Antigonus II Gonatas in the early to mid-3rd century, composed a didactic poem known as the Phenomena. It chiefly deals with the constellations and the movement of celestial bodies, based on the teachings of Eudoxus of Cnidus. In Alexandria, a new constellation was discovered by the astronomer Conon of Samos, and named Coma Berenices, or the Lock of Berenike, in honor of Queen Berenike II, which became subject to a poem of the famous court poet Callimachus during the mid-3rd century. The movement of heavenly bodies and stars was directly associated with another important aspect, timekeeping. Measuring the passage of time was vital when it came to marking the seasons for farming, determining the length of a political office, or when to host festivals. Unfortunately, there were few universally agreed principles on how the passage of time was to be tracked, especially when it came to factoring in lunar and solar cycles. The Egyptians created a solar calendar of 365 days, with 12 months of 30 days and 5 days added to the end of the year, along with a 6th day every 4th year, since the Earth takes 365 and a quarter days to fully orbit the Sun. In Babylon, a lunar calendar of 12 months with a total of 354 days occasionally had a 13th month, the intercalary, inserted every 2 to 3 years to line it up with the solar year. Without a unifying government to enforce a single calendar, the systems used by Greek city-states during the Archaic and Classical periods were even more varied. Most calendars were based on the lunar model, but would incorporate solar elements into it, making them lunisolar, resulting in years of 12 or 13 months with 29 or 30 days per month. This is where the similarities begin to fall apart. The Athenian New Year began in the month of Hekatombion, roughly July or August in our calendar, whereas in Macedonia, the New Year was in their month of Dios, our October. The names of each month were not consistent between the regions either, and could be changed depending on the situation. In one notable instance, the Athenians twice renamed the month of Munikion, April or May, so Demetrius Poliarchides could be inducted into the Eleusinian mysteries during his stay in Athens, once so he could perform the initiation rituals, then a second time to allow him to participate in the actual mysteries themselves, all in one single go. Following Alexander's conquests, there was a change in how calendars were organized. The most obvious adjustments were in the kingdoms of the Greek East. Seleucid calendars adopted the Babylonian model because it was much more regular, but changed the Babylonian month names to Macedonian ones and started their new year in October, rather than April. The Babylonian calendar was more accurate because they had long incorporated the Metonic cycle, a phenomenon which recognized how 19 solar years is almost the same duration as 235 lunar months, which kept it more synchronized. This Macedonian-Babylonian calendar found its way into India, where it remained in use during the Indo-Greek kingdoms through the Kushan period in the 3rd century AD. The Ptolemy stayed consistent to the traditional Egyptian model, but the decree of Canopus shows an attempt to make it 365 and a quarter days per year, though this ultimately petered out without any real success. In Greece, we can say that things became more uniform, as the rise of federal leagues like Aetolia and the Achaeans standardized calendars from multiple city-states. They did add another way to track the years. Shortly after Alexander arrived in Babylon, the findings of the Babylonians were recorded and read by an astronomer named Callippus of Cyzicus, who proposed the so-called Calippic cycle. Essentially, Callippus realized that the 19-year cycle of Meton could be improved upon by factoring in the quarter day in each solar year, so by multiplying it by 4 and subtracting 1 day from the final 19-year cycle, you would end up with a total cycle of 76 years. It was probably more useful to an astronomer than in civil administration, but was an advancement nevertheless. The situation was similar in the Roman Republic. However, by 46 BC, the lunisolar calendar used in Rome of 355 days per year, plus an additional month on alternate years, had become severely out of sync. Then dictator Julius Caesar tackled this problem with the assistance of Cleopatra's court astronomer Sosigenes by introducing the so-called Julian calendar, which adjusted the number of days per year to 365, plus an additional day every 4 years. This involved the insertion of 90 days into the year 46 BC, a total of 445 days to compensate for the lack of synchronization, whereupon the first day of 45 BC onwards is more or less in tune with what we have in the modern Gregorian calendar. In the decades following, this system was amended again by the Emperor Augustus in 8 BC, most notably with the months of Quintilis and Sextilis, which were renamed to Julius and Augustus in honor of his adoptive father and himself. The influence of the Julian calendar remained limited in the Hellenistic East for the next several centuries. Its inhabitants stayed faithful to the preferred systems that they used, and the Romans pressed very little on the matter until the end of late antiquity. For most of the ancient world, chronology was determined by political office. In Rome and Athens, dates were in reference to who served as that year's consul or archon respectively, while record-keeping in the monarchies tended to use the regnal date of the kings and queens, for example, in year 3 of Ptolemy IV. This differs from our conception of linear and continuously measured time, which is employed by most of the modern world in some form or another, with the dominant model being the Gregorian calendar, which reckons us to be in the year 2024 AD in the time of this episode. This innovation can actually be traced back to the Seleucid Empire, which saw the introduction of the Seleucid era. The year 312-311 became year 0, as the monarchy considered that date to be the empire's foundation by Seleucus I following his return to Babylon, and the count would survive each successive Seleucid king rather than resetting at the beginning of a new reign. When the kingdom was finally annexed by Pompey in 63 BC, it was reckoned as 249-250 in the Seleucid era. It proved to be highly influential, as those like the Parthians and Judeans would follow suit with their own eras, and in turn this served as the model for the Christian Anno Domini or the Islamic Hijri. The Seleucid era lasted far longer than the dynasty itself, as Nestorian Christians living in China continued to use it on their gravestones during the 15th century AD. Calendars are good at the broader measurement of time, but what about devices that help determine smaller windows, such as the hour of the day? The symbol of all of these was the sundial, a device that Herodotus attributed to the Babylonians, but was used extensively in Egypt as well. These come in different forms. The traditional model is a flat circle divided up into different parts with an elevated pointer, the gnomon, which casts a shadow over the hourly divisions. Another common type is the hemicyclium sundial, a design with a hemicycle shape imprinted onto a stone that resembles an altar, with the gnomon casting a shadow into the impression. Aristarchus is said to have created new designs that were a bit more precise and functional, as did Berosus. One anonymous author joked that everyone carried their own portable sundials anyways, since, quote, "If you put your nose pointed to the sun and open your mouth wide, you will show all passers-by the time of day." In Athens, one of the most prominent features of the Roman agora is a large octagonal marble structure known as the Tower of Winds. The name is due to the large reliefs on top of the walls, each image depicting one of the 8 gods of the wind, Boreas, Zephyrus, and so on. This structure was likely built by the Macedonian astronomer Andronicus of Cyrene during the late 2nd century BC, and it is the only example of a clock tower to survive from antiquity. Appropriately, it contained 8 sundials on the outer wall, useful given its proximity to the local marketplace. Inside featured a water clock, the evidence of which can be still seen on the marks on the floor. Yet of all these devices, few are as famous or radically altered our understanding of the technology of the ancient Greeks as the Antikythera Mechanism. In 1900, sponge divers sailing discovered a shipwreck adjacent to the small island of Antikythera, about 150 kilometers north of Crete. Evidence suggests that it sank between 70 and 60 BC, and the contents of the ship revealed a treasure trove of bronze and marble statues, luxury furniture, and even a red marble sarcophagus. All of these were remarkable finds in themselves, but what proved to be the most thought-provoking of the artifacts were misshapen lumps of stone and metal, but further inspection revealed that these were no mere scraps of bronze. By looking at the stone at careful detail, a clear imprint of a mechanical gear, along with a bit of Greek script, is clearly visible. Little did they know, but the sailors held in their hands the oldest known analog computer to ever be constructed. Its survival is astonishing, as it is said that one of the sailors on the expedition intended to throw it back overboard thinking it was just a rock dredged up from the deep, only to be stopped by the admiral who noticed metal among the calcified stone. A total of 82 fragments have been found, with 3 of the largest fragments now on permanent display in the National Archaeological Museum of Athens. After sitting at the bottom of the ocean for 2,000 years, time has compressed and corroded much of the device's features, and the fragments make up only 1/3 of the original object. It remained an enigma to the earliest investigators, but with each passing decade, new imaging technology has allowed for the scanning and cross-examination of its inner workings. For the most part, I'm following the reconstruction presented in the excellent work A Portable Cosmos by Alexander Jones, which gives a complete account of the history of the mechanism and an explanation of the science behind it. Firstly, the mechanism was contained in a wooden box with a bronze front plate, back plate, and a cover for each side, a total size of about 13 by 7 by 3.5 inches, 34 by 18 by 9 centimeters. A total of 6 dials are present on the mechanism, 5 on the back panel and 1 on the front panel, all with pointers that rotated around them when their inner gears moved. Starting with the back panel, the first is the Metonic cycle, which have radial lines divided into 235 cells, each inscribed with the name of a month from the Metonic calendar. The Metonic calendar is a Greek lunisolar calendar with 12 years of 12 months, and 7 years of 13 months, so a total of 235 months equaling to 1 month per cell for a complete cycle of 19 years. Within the confines of the Metonic dial is the smaller Olympiad dial, divided into 4 equal quadrants to represent the Pan-Hellenic festivals held in each year: the Olympic, the Nemean, Isthmian, Pythian, and Haliaean games. Below the Metonic is a small third dial, the Callipic dial, which contained a calendar which counted 19-year cycles within a complete cycle of 76 years. The large fourth dial is the Saros dial, which is similar in design to the Metonic, containing 223 cells in a series of radial lines. However, most entries are devoid of text, but are occasionally marked by a lunar or solar eclipse, with each cell representing a lunar month, a total of 18 solar years. Last is the Exelios dial, which was split into 3 equal parts, listing nothing, 8, and 16, each a multiple of 8-hour segments added to the time of the celestial event recorded in the Saros dial. On the front panel, only 1 large dial is present. However, multiple pointers representing the planets, the sun, and the moon would rotate clockwise around the center, presumably representing the Earth. Surrounding the dial were 2 scales forming rings. The inner scale consisted of 12 divisions, each representing signs of the zodiac, and a total of 30 notches marked the days. By contrast, the outer scale was based on the Egyptian solar calendar, with 12 equal months containing 30 notches each, and a 13th segment containing only 5 notches, which adds up to a total of 365 days. The back cover held a bronze slate containing an inscription, of which only 50 lines are legible after being impressed into the metal of the back dials. They essentially describe what the mechanism is calculating, namely the movements of the moon and sun along with a description of the cosmos. Other inscriptions like the movement of the stars and planets could be found on the front. The internal system of the device is a startling display of the mechanical science that flourished during the Hellenistic period. It is estimated that upwards of 64 individual gears were linked together, which could be manipulated by the user with a knob on the side of the device. The number of teeth on the gears varied in size, but the largest fragment shows a gear possessing 223 teeth. In summation, the mechanism could be used to calculate several parameters: the phase and age of the moon, the ecliptic coordinates of the sun and moon, the timing of eclipses, the rising and setting of constellations and major stars, the synodic phases of planets, and the cycles of the Olympiads. The Antikythera Mechanism is one of the most remarkable artifacts that has ever been discovered. It represented a synthesis of Greek, Egyptian, and Babylonian astronomical knowledge into one complete package. The complexity of its mechanisms has led to a dramatic re-evaluation of the technological sophistication of the ancient world. Yet we are left with many questions. Where did the mechanism come from? Who built it? What is the purpose of the device? How unique is it? Perhaps this last inquiry is a good place to start. In all the treatises and instructional guides that have come down to us, none describe anything that exactly resembles the Antikythera Mechanism. Such was the complexity of its design that it is only rivaled by later instruments constructed during the late Middle Ages, roughly 1400 years later. Yet it would be rash to suggest that it was a one-of-a-kind object, and is instead better understood as a logical progression of Hellenistic science. One of our earliest references to a physical model of the universe comes from the works of Cicero. According to the famed orator, Archimedes had constructed two types of objects known as sphera, or planetariums. One was a three-dimensional celestial globe of such beauty that it was taken by the consul Marcellus and placed in the Temple of Virtue in Rome following the sack of Syracuse. The second was a mechanical planetarium, capable of showing the movement of the sun and moon, along with 5 stars which he calls wanderers. He also attributed a similar device to Posidonius of Apamea, a prominent Stoic polymath and astronomer who was active during the early 1st century BC. Based on the dating of the shipwreck, some have suggested that the mechanism was one of Posidonius's, but this is unlikely. We have learned from the writings of those like Hero and Philo that the mechanical prowess of the Greeks was becoming extremely proficient at this time, and historians have concluded that the creation of such a device was certainly possible in a contemporary workshop, probably in the early 1st century BC. There are elements of the mechanism that can hint to its geographical origins. One noticeable clue is that the Metonic calendar on the back appears to be based on the Corinthian version. This could mean that it was destined for Corinth itself, or perhaps one of its colonies, like Syracuse, which links it to the Archimedean tradition. A further investigation into the inscriptions show that the names of the months are based more on an Epirot dialect, and it just so happens that the city of Apollonia bordering Epirus was a Corinthian colony, meaning that the device was likely commissioned by someone from the area. The choice to include the Haliaean Games on the Olympiad dial is also curious, since this relatively obscure Pan-Hellenic festival is only celebrated in Rhodes, a possible location for its construction. It may be no small coincidence that Posidonius spent much of his career teaching in Rhodes, and he could have commissioned the same workshops to build his planetarium only a few years later. The mechanism's purpose is tied up with the possible identity of whomever owned it. Obviously, it had to have been commissioned by someone who was wealthy enough to compensate for the amount of labor and technical specialization to build it. The functions of the device are suited more for the demonstration of astronomical theories to an educated individual looking to learn more about them. The information provided would have been impractical for those looking to use it in maritime navigation, and it would have been an expensive device to use for charting horoscopes if one takes an astrological approach. There are a handful of important takeaways. The Antikythera Mechanism was a special device, but not one that is light years beyond the technology of the time. There is clear evidence of other similar models representing the cosmos being built during the Hellenistic and later Roman period, which have not survived given their delicate materials and cost-prohibitive nature. It was an incredible piece of engineering that was very much in the tradition of Alexandrian mechanical science, represented by the writings of those like Philo, Hero, and Ctesibius. It represented a culmination of astronomical knowledge achieved during the Hellenistic period. Aspects of Babylonian and Egyptian teachings make their appearance, and the insights of Hellenistic astronomers like Callippus and Hipparchus. In some sense, it is emblematic of the era itself.